Section 15.4, we're going to be talking about trees, and no, this is not the kind of tree that grows in the ground. A tree is a graph that is connected, has no circuits. One way of saying the same thing is a tree is a graph in which each pair of vertices can be joined by one and only one path. A tree is a connected graph in which every edge is a bridge. A tree is a connected graph with n vertices and n minus 1 edges. So these are all saying exactly the same thing. Which of the following graphs are trees? Why or why not? Well, this one is not going to be a tree because it is not connected. We have this vertex over here which is not connected. If you look at this graph, it's not a tree because we have these edges are not all bridges. We have a circuit. This in the middle is a tree. Every edge is a bridge. All the vertices are connected, and there are no circuits. A subgraph is a set of vertices and edges chosen from among those of the original. So if we call this the original graph, and I remove this edge right here, that is a subgraph, one possible subgraph. If I start with the original graph and remove this edge, I have a different subgraph. A subgraph that contains all of a connected graph's vertices is connected and contains no circuits is called a spanning tree. The two subgraphs in the previous example are examples of spanning trees. Find a spanning tree for the graph below. So what we're looking for is a graph that is connected, and we don't want to get rid of any of the original vertices, and we don't want any circuits. So let's suppose we get rid of this edge. If we get rid of this edge, let's get rid of this edge. And maybe this one. So what do we have right now? We've got A, B, E, F, H, G, D, and C, and let's see what edges we still have. We've got from A to B, B to C, G to F, G to H, H to E, and I need to get rid of one more edge because this would make a circuit. So let me get rid of A to D. So I'll get rid of A to D. And now I have all the original vertices. And it's connected and there's no circuits. This is a different example of a spanning tree using the same graph. Minimum spanning tree for a weighted graph is a spanning tree with the smallest possible total weight. From the spanning trees below, C has a smaller weight than B, but is this the minimum spanning tree, or do we have to try more spanning trees to figure out which one is the smallest? There is a way of finding minimum spanning trees using what we call Kruskal's algorithm. First thing you want to do is find the edge with the smallest weight. If there's more than one, pick one at random and mark it. Find the next smallest edge. It does not have to be connected or adjacent to the original edge. Mark that one. Keep finding the next smallest edge, but remember, we cannot create a circuit. Repeat until all vertices have been included, and then this will give us a minimum spanning tree. So let's suppose we have 7 buildings on a college and they are connected by sidewalks. The weighted graph represents buildings as vertices, sidewalks as edges, and the sidewalk lengths as weights. A heavy snow has fallen and the sidewalks need to be cleared quickly. Campus decides to clear as little as possible and still ensure the students walking from building to building will be able to do so along cleared paths. Determine the shortest series of sidewalks to clear. What is the total length? So here we have the campus modeled in a graph, and we want to use Kruskal's algorithm to find a minimum spanning tree. So the first thing we have to do is find the shortest sidewalk, and we look at these numbers right here at the weights, and we have a weight of, let's see what the smallest one is, 242. Okay, so we're going to take that edge, we're going to highlight it. The book says use red, but any highlight will be fine. Then we're going to find the next smallest edge, and it does not have to be connected to the original edge of the 242. So let's do this one is the next smallest at 245. And then we have 249 is the next smallest. We have to check to make sure that our graph is connected and we've used all the vertices, which it's not yet. So now we're going to look for the next smallest edge. The next smallest, we've got a 251 and we've got a 251. Well, we can take either edge as long as we don't make a circuit. If I were to pick this edge right here, that would create a circuit, so we don't want to pick that one. So we're going to choose this edge right here. Now we're going to look for the next smallest. The next smallest is 253, and we're going to check to see if it makes a circuit, and it does not. And we still haven't included vertex E, so look for the next smallest. After 253 is 255, but that would create a circuit, so we're going to ignore that one. Next smallest is 256, but again that would create a circuit, so we're going to ignore that one. Next smallest is 259, and that does not create a circuit, so we have now included every vertex. So this would be our minimum spanning tree. We would add up the edges. So we have this plus this plus this. We would add up those weights, and that would give us our minimum spanning tree. When you add it up, you get 1,499 feet. And the homework is 2 through 32 even. I also want you to do problem number 44.